Hello, chemistry students. In this class, we are going to do a lot of experiments, and we're even going to ask you to develop some of your own. So it's important that you understand the components of good experimental design. We're going to start by talking about scientific inquiry. This is where you observe the world around you and you start asking questions in order to figure out how it works. Making observations and asking questions about your environment are actually the first two steps of the scientific method. Now, in the past, you may have learned the scientific method is a linear process, one that has a beginning and an end. But actually, the most important feature of the scientific method is that it's a cycle, that the end brings you right back to the beginning. Because at the conclusion of an experiment, a good scientist is going to look at those results and decide, do these really support what I said at the beginning? Or does my hypothesis have to be revised? Does my question have to be revised? Or maybe it's not the question that has to be changed, but maybe it's the procedure that you followed in order to support that statement. So the scientific method is a cycle. The end is going to lead you back to the beginning in order to allow you to do revisions and revisions and revisions. So I mentioned the word hypothesis. A hypothesis is the result of the observation and the questioning process. In this class, we'll also call hypotheses claims or predictions. You see, whenever you're looking at a scenario, you're usually wondering, well, does one thing cause another? Or how is thing A related to thing B? Well, forming your claim or your prediction and then devising an experiment in order to support or refute that is going to help you explore those relationships better. The two things that you're usually curious about, whether or not they have a relationship to each other or not, are called variables. There are two experimental variables that you need to know, an independent variable and a dependent variable. The independent variable, which I have here in green, is what you, the scientist, changes, and the dependent variable here in gold is the consequence of that change. So if you look at the claim at the bottom of the screen, you'll see that I colored the independent variable green and the dependent variable gold again so that they match. And what I, the scientist, am changing is the amount of sleep I get before a test. And what I'm going to measure is the grade that I get on the test. So is there a relationship between the amount of sleep I get and the grade that I get on a test? Let's take a look at another one. Using Neosporin on a cut will make it heal faster. Neosporin is a cream that has an antibiotic in it. And so our independent variable would be whether we're using Neosporin on a cut or not. And the dependent variable, what we'll measure then, is the speed at which our cut heals. So in order to explore the relationship between our independent variable and our dependent variable, we need to devise an experiment. An experiment is a situation that is deliberately set up in order to isolate our independent and dependent variables to really see if they are related to one another, and if so, how. You have to remember that the results of your experiment may change your original claim, which means that you could be wrong. And there's a lot of wrong in science. But again, that's why it's so important to recognize that the scientific method is a cycle and it's not linear. You have to keep on going and asking and revising until you arrive at your truth. All right, so we talked about experimental variables, but with this example, we're also going to talk a little bit about control variables. So let's take a look at this claim. Sugar will dissolve faster in hot water than in cold water. My independent variable is the temperature of the water, and my dependent variable is how quickly the sugar dissolves. So if we take a look at these pictures, I have 3 different trials in my one experiment here. Trial A, B, and C. And here I have 25 degrees Celsius is the temperature of water in A, 45 degrees Celsius in B, and 35 degrees Celsius in C. And then I have the sugar, 5 grams in A, 2 grams in B, and 8 grams in C. I also have the amounts of water here. And then I have my results. 53 seconds in 25-degree water, 35 seconds in 45-degree water, and 47 seconds in 35-degree water. So I ask you, does this look right to you? Well, I can tell you it sure doesn't look right to me, because I can't tell if the sugar dissolved fast in trial B because of the temperature of the water or because I used the least amount of sugar in that trial. So this experiment is rather sloppy. It doesn't follow good experimental design. In order to design a good experiment, you need to change only one thing and make that thing your independent variable. That way, you are isolating that independent variable, and you're able to tell if the consequence or the results of your experiment are because of that change. When you have something like what you see on the screen now, you don't know if the sugar dissolved the fastest in trial B because of the temperature, or because of the amount of water, or because of the sugar, because it's different for every single trial. That is not good experimental design. You need to have some control variables. Control variables are things that you leave exactly the same throughout the entire experiment. So I fixed it, and if you notice now, the only thing that has changed from trial A to B to C is the temperature of my water. The amount of sugar is the same, the amount of water is the same, and then of course I have my results. And I can deduce that in trial B, the sugar has dissolved the fastest because of the temperature, because that was the only thing that's different from trial C and trial A. And therefore, I have supported my claim that sugar will dissolve faster in hot water than in cold water. Now, in this class, we're going to ask you to fill out claim evidence reasoning tables, where you have to state your claim, support it with evidence from your experiment, and then explain the reasoning behind it. So our claim is sugar will dissolve faster in hot water than cold water. You know that already. And then look at my evidence. I say room temperature is 25. The sugar dissolved faster, 32 seconds in 45-degree water, and it took longer to dissolve, 44 seconds, in 35-degree water. There's something missing from this evidence. I'm sure you can spot it. I didn't put the time for how long it took the sugar to dissolve in my cold temperature. And so I couldn't get full credit on this claim evidence reasoning table because I don't have all of the evidence necessary to support my claim. Now let's look at our reasoning at the bottom. I say higher temperatures make molecules move around and collide faster, causing the sugar to dissolve faster. This is a good piece of reasoning. I know that a lot of students are going to write things like, yeah, the sugar dissolves faster in hot water. That's great. That's only a part of it. You have to kind of expand on that and find a reason why. And so that's why you have to tell me a little bit more. Why do you think this is actually happening? So this is a pretty good claim evidence reasoning table. I'm not going to get full credit on it, but if I make just one little tweak, then I can get all the points on it. All right, so there are two types of data that we're going to be using in this class. Qualitative data means that you are describing the data or maybe providing a picture or a photo, whereas quantitative data means that you are providing numeric data. So the time that it took for the sugar to dissolve in each cup, that is an example of numeric data because time is expressed in numbers. Now, remember that there are two characteristics of scientific evidence that you're striving for in your experiments. Number one, it has to be objective, which basically means that you can only describe exactly what happened in your experiment. Please do not fudge your data in order to support your hypothesis. That is not good science. That's being unethical and dishonest. You need to report exactly what happened, whether it proves you right or it proves you wrong, because other people could learn from that later on down the line. But the other thing about good scientific evidence is that it is repeatable. So your procedure has to be repeatable by other people. You will know yourself if you have a repeatable procedure, if you do your experiment again and again and again, and you continuously get similar results. But if you repeat your experiment over and over and you get way different numbers, you've got to go back and look at that procedure and tweak it in order to tighten it up a little bit so that it is repeatable not only by you but by other people as well. So good experimental design contains multiple trials, about 3 to 5 to be exact. And when you have multiple trials, it's going to help you to determine whether your procedure is repeatable or not. And like I said, if you get similar results, then each time, then that means that you have a repeatable procedure. So I want to refer back to my sugar water experiment because in my view, like that example was good for what I was using it for. But if I were really going to do it in the lab, this is what my data table would look like. And so here I have trial 1, 2, and 3, but I'm doing it 3 different times. So in trial 1, my time for the sugar to dissolve was 53 seconds the first time I tried it, 60 seconds the second time I tried it, and then 58 seconds the third time that I tried it. For trial 2, for the room temperature water, which was I think 25 degrees Celsius, the first time it took 44 seconds for the sugar to dissolve. The second time, 44 seconds for the sugar to dissolve, and then 41 for the second. And then I've got 3 different tries for the hot water as well. This is what I mean by having multiple trials. Multiple trials didn't mean, okay, do 1 cold, 1 room temperature, and 1 hot, and let's call it a day. No, you've got to do multiple experiments in order to ensure that your procedure is repeatable, to ensure that your data is repeatable. What this is going to do then, and I mean, like you saw, I had 3 different trials, and I had 9 different pieces of data. And so what we do in order to boil down the data into one number is that we will average the data. This is going to make it easier to make comparisons from one experiment to the next, and all of your data is given equal weight. One drawback is this. Let's say I was doing my experiment and I knocked over the cup of water with my elbow and some of the water spilled out onto my lab table. Well, that could affect the rate at which the sugar was dissolving, and then that could make my data look a little bit different than what it really should look like. So that's called an outlier, and you have to be careful of outliers because they can artificially skew your data. And so once I add my average row here at the bottom, you can see that I just added these 3 numbers together and divided by 3, and now I have a single data point. So, the average time that it took for sugar to dissolve in the cold water was 57 seconds. And so some of the trials may have been a little bit more, some of them may have been a little bit less, but the middle point of those trials was 57 seconds. All right, at this point, I'm going to stop this video, and you guys are going to practice some experimental design on another document. Thank you so much for watching my video, and I'll see you all in class. Bye.